This video is presented to you by Physics for Students. To know more, please visit us at physicsforstudents.com.
Hello, welcome to this new video on tensor calculus. Well, I would like to tell you that this is basically an extension or the second part of the metric tensor video that I have made a few days earlier on the topic of general theory of relativity. First of all, let me thank all the subscribers because Physics for Students slowly has now reached to the number of 3,000 subscribers. So my sincere thanks, gratitude and best wishes to every single subscriber who has made this possible. Starting with the topic of metric tensor, first of all what I would like to tell you is that the basic derivation of metric tensor is provided in my earlier video, which is there in the playlist. I also have provided the link in the I button. You can just click on there, and if you really want to go back and study the derivation and further details, conceptual as well as based on intuition, what metric tensor is, you can do it from the earlier video. So first of all, let us go and get a quick recap so that for those who are watching this video for the first time, it doesn't come as a difficulty. Going back to this topic of metric tensor, now this particular equation which you can see, this is something which we have already derived, okay, in the previous video. So if you're looking for derivation, you can go back and understand what it is all about. However, the particular subject of emphasis for this video is to deal a little bit more about this particular metric tensor, the invariance and other properties. Note that what you need to understand that metric tensor is a fundamental object of study in the general theory of relativity. So those who are willing, or those aspirants who are really willing to study general relativity, you need to have a complete grasp of metric tensor, and that is the subject of today's video. So we will go further details in understanding what this metric tensor is all about. Now you understand that this is basically a generalization of the gravitational potential of Newtonian gravitation. These things I have already discussed in my earlier video. So you can tell that it actually captures all the geometric and causal structure of space-time. It defines, distance, volume, curvature and many other things. So this is what is metric tensor, already defined and derived. However, a quick recap will help you formulate those ideas, and then we will venture forward. Now the metric tensor that we know is actually something which arithmetizes the space. That means given a space, if we want to frame certain rules, what are the ways in things will change, angles, other things, metric tensor is basically the object for that. So we denote it by small g, and this is particularly measured for contravariant. So you will always find the indices going up for the contravariant, going down for covariant, and this is the basis vector. Now let us consider the 2 points, for example on the right hand side of the screen, ds, okay, by an infinite similar small distance, which is this ds. And now if there is a vector dr which extends from one point to another, then the square of the differential length can be given by this one, right? So the vector the ds square, we are using the dot, so it can be written in this way. Now this vector can be written using contravariant components, which is this, or using covariant components, which is this. Okay, so this is it can be written in either way, and it can be written further into this, which leads to this, and it leads to this. If you really want to have an understanding further, you can go back to my video, but this is, I think this is good enough to give you an understanding of what we are dealing with. So you see this g sub ij, I should call it, is a covariant component of the metric tensor, right? So this is how it happens given an infinite similar distance and using the dot product. So we can use, because we are involving the dot product of dr, so we have the option of using the contravariant components in this way. Now proceeding further, we can use the same covariant component and we can proceed in this way. We get the results at this, and this is basically the contravariant component of the metric tensor. So this is called indices jumping, which those who are aware about tensor analysis you know, so nothing new to tell you about. So this is how the earlier was the covariant, and using the covariant we can use the contravariant part. Now we can use both, right? We can use both contra and covariant components. So you see the contra and co, I have underlined it in red. So it comes to this and this. And as you see that we do not need the metric tensor if we put these values, right? So if we really don't need metric tensor, and this is why we don't need the metric tensor. This is laid out there. So let us go to the next part so that we can understand. Now you see this ds square. Okay, this ds square, it can be written in this three way. First of all, this one using the contra, and then the first is the covariant, then it comes to the contravariant, and then it comes both the upper and lower indices, that is the mixed tensor. Now the basic thing that you need to understand, that whatever the way ds square is written, okay, it is a co or a contra or a mixed tensor, one thing is sure, that the task of the metric tensor and its component g sub ij or g super ij or mixed or anything is to turn the product of incremental coordinate changes expressed either in contravariant or covariant as the invariant distance between those 2 points, maybe a and b. So that is the beauty of the metric tensor, as it provides the geometry of the space. So the distance between the points are always the same, irrespective of the coordinate system that we use and irrespective of the values that ds square provides, either it is covariant or a contravariant or a mixed. So this is a quick recap in order to let you know what we really did in the last video, so that you understand that this part, which is telling that it is the what you call invariant part, this is something which you're going to take up, and we are going to prove in the video why and how it can be proved that it's invariant, plus some other properties and some other knowledge about tensor calculus. Okay, so first, before we go ahead, I just wanted to have, because you guys already know, because you were aware about calculus, but just a quick recap in what we know is a total differential. I have laid down a very basic definition of total differential. The differential of a function of two or more variables, when each of the variable receives an increment. The total differential of the function is the sum of all the partial differentials. This is just a very basic definition, but let us quickly recap on the total differential part and why it is important. We will see in a few minutes from now. Now, we studied differentials. We know that. Now, if, for example, we state that this y equals to fx and f is differentiable, right, then it leads to this, obviously dy equals to this part, right? So we know that this is an important use of this differential is in integration by substitution. I'm not going ahead. Now another important application is the approximation part. Now what do I mean by approximation? Say for example, delta x equals to dx represents a change in x when dx is small change in x, right? And this dy delta y is the change in y resulting from the change in x. Now fundamental, what we need to understand is this, that as dx gets small, right, as dx gets small, the difference between delta y and dy also tends to go towards 0. So we can tell in this way also that as dx goes to 0, the error in approximation delta y with dy also goes to 0. Now apart from that, okay, if we want to extend this idea to two variables, so here we are with two variables, let us see what it happens. So we get z equal to fx comma y, so we have taken two variables and let delta x equal to this and delta y equal to dy represents changes in x and y respectively, and let delta z equal to f function of x plus dx, y plus dy minus fxy be the change in z over the change in x and y. Now let us remember also that what we learned is that f sub x and f sub y gives the instantaneous rate of x change. It's in the x and y direction respectively, right? So we can approximate this delta z with dz equal to this one. In other words, we can say that the total change in z is approximately the change caused by changing x plus addition the change caused by changing in y. So I've just put it in words. The total change in z is approximately the change caused by changing x plus the change caused by changing in y. Now let us suppose that this is a function on a continuous open set. I've called this set S, you can call it anything, and let dx and dy represents a change in x and y respectively. Then where the partial differentials of f sub x and f sub y exist, then the total differential is given by this. Okay, this is the total differential, this one. So the total differential, what I mean to say by the last line is that it is, you will see that it is very close to the chain rule in structure. Why? Because for a function of two or more independent variables, the total differential of the function is always the sum over of all the independent variables of the partial derivative of the function with respect to, which we write WR2, with respect to a variable times the total differential of that variable. Right, so let us see further for an example. So let me repeat, the total differential is something which is close to the chain rule. For a function of two or more independent variables, the total differential is the function is the sum over of all the independent variables of the partial derivative of the function with respect to a variable times the total differential of that variable, right? So now for example, we give a function f of x this, then the total differential is given this. If we get a function with three variables, we get this, and if we get a function of this, we get this, right? So now one thing which you need to understand is that one of the most important relations involving continuous functions of multiple continuous variables such as coordinates or others is the formula of the total differential. Now okay, so this is more or less, you can see this is a structure which I'm using that curly d sign. So for f of x y z, this should be notation in curly notation. This is something looks like this, just to give you a basic idea. Now say for example, if in general if you are given a, say for example, a smooth function, okay, f y equals to f x1 x2 goes up to n, the incremental change of dy in the variable y, which results from incremental changes in dx1 2 3 up to n, is given by this, right? This. So here what happens is that dy is basically called the scalar quantity. It is called the total differential of y. Now the formula actually expresses the fact that the total incremental change in y equals the sum of the sensitivities. That means what will, I mean to say the sensitive parts, those which will change to the independent variables applied by the respective incremental changes in the other variables. Now if we go forward and if we write the vectors in this way, now you see I have taken abrupt numbers or abrupt variables deliberately. I will tell you why it is the reason, just follow it out. So we define these vectors in this way, then dy actually is equals to the scalar, that is the dot product of those two vectors, right? That is, we have dy equal to g dot d. Now regarding the variables of x1 x2 up to n, xn for example, if you take this one, then this defines the scalar field on the manifold. You can just ignore manifold if you think it is confusing. It is a scalar field, and these variables are basically the coordinates on the manifold. Why I'm telling manifold? Because we are dealing with general relativity, which primarily deals with manifold. So these figures which it relates to the coordinates of the manifold, and you will see that g is the gradient of y, which is given by this Greek nabla sign, right? G is the gradient of y and d is the differential position of x. it can also be written as dx, whatever. Now all of them are evaluated with a point of x1, x2 dot 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 up to xn. Now this gradient g equals to nabla y is an example which is called a covariant tensor, and the differential position d equals to dx is an example of contravariant tensor. So the difference between these two kinds of tensors, I mean to say co and contra, and how they transform, this is a subject matter which we will now see, and which is called the law of transformation. Now why we need the law of transformation? Because unless we understand the law of transformation, how the partial derivatives behave with the tensors, we are not in a position to understand metric tensor properly. Now suppose we have a smooth continuous coordinates which I have denoted with capital X and defined in the same manifold. Now each of these new coordinates can be expressed in the region, I mean to say, as a function of the original coordinates. So I call them xi. You can call it anything that you like. So the total differentials of the new coordinate can be represented as this, right? So now you understand why I told you this chain rule is similar to chain rule, and why we need to know the rules. Now say for example, if we denote capital D, okay, I mean to say we are denoting it by vector. So letting D as the vector, we see that the components of capital D are related to the components of small d by this equation. You can take a snapshot if you want. You can just look into it. Capital D, which is represented by small d, can be represented, and this is actually the prototype or a sample transformation rule for a contravariant tensor of the first order. Now why I have taken first order? Because it will be easy to explain, it will be easy as an example, and it will be easy for you to understand. So d with respect to small d, how, and this is how it happens, and this is basically a rule of transformation for contravariant tensor of first order. Now on the other hand, if we take g equals to nabla y, it is a covariant tensor, so we get it. So it doesn't transform according with this rule, right? So to find the correct transformation rule for the gradient, we need to look into the Jacobian, which is not a zero. But anyhow, the original coordinates can be expressed as some function of these new coordinates, which is this one. Again, I am using the capital X within the braces for I equals to 1, 2, 2, 3, 4 up to n, and this enables us this one to enable to write the differentials of the original coordinate at this. Okay, we are using the same rule. I hope that things are clear till now. Now if we substitute these expression, I mean to say this one which you see right on the in front of your screen with this one. So we substitute with this arrow, which I have marked it in red, into this equation and collect. Somehow I have skipped those parts. You can do it manually by differentials of the new coordinates. We get something like this. Right, so we use the sigma notation, we get that. So the components of the gradient of g of y, now you see this is what I have written, gradient of g with respect to xi, x superscript I coordinates, are given by the quantities in parentheses, that means within the braces, right? And if we let g denote the gradient of y with respect to these new coordinates, let us go to the next screen. We have denoted now capital G to denote the gradient of y with respect to the new coordinates, right? These are the new coordinates. So we get this one. Now this is actually the prototype rule of transformation of covariant tensor of the first order. Now let us compare this the prototype rule of covariant of first order and contravariant. Now one thing you need to understand, that these two, when we compare this with the contravariant rule which we have just seen, we see that they both define and they transform components as linear combinations of the original components. But I think if you can go back to my tensor videos earlier, I have shown that more precisely. But anyway, in the contravariant case, the coefficients of the partials, now you see, for example, the contravariant is the coefficient of the partials of the new coordinates with respect to the old coordinates. That is why it is called contra. And in my tensor analysis video, I have shown that it is got a backward and a forward transformation just to make things easy. Whereas the covariant case, you will see that the coefficients of the partials of the old coordinates, this one, small x, with the old one. So this is just to let you know that the original components of contravariant case, the coefficients are the partials of new with respect to old, whereas covariant is just the opposite. It is the partials of the old with the new. Now here I would like to mention something which is worth mentioning, that the key attribute of a tensor is that its representations in different coordinate systems, and it depends only on the relative orientation and scales of the coordinates axis at that point, not on the absolute values of the coordinates. Right? It is relative orientation and scales of the coordinate axis at the point, not on the absolute values of the coordinates. What I mean is that the absolute position vector pointing from the origin, for example x, to a particular object in space, is not a tensor, because the components of its representations depend on the absolute values of the coordinates. In contrast, the coordinate differentials transfer based on the local information or whatever the local rules set it. So good as for now. Our next part we would be dealing with the same contra and covariant, but this is must of a loose definition. So we want to make it a little bit more rigid before we jump into the metric tensor part. So we will start with the co and contravariant tensor of rank 1, and what we see is that, let us say x be a coordinate system. Okay, x1, 1, 2, 1, 2, 3, 4, and it goes up to, for this, for x coordinate system, and x prime 1, prime 2, prime 3 goes up to x prime I or x prime n be the coordinates of the y coordinate system, and let a prime I equals to 1, 2 for a prime 1, 2, 3 be the n functions of the coordinates of x1, x2 in the x coordinate system. Now if the quantities of ai, that is, now you have to be a little bit careful, because there will be change in terms of indices, and that is the beauty of tensors. So if the quantities of a prime are transferred to a prime I in y coordinate system, then as per the law of transformation which we have seen, this is something which happens. And it can be also written as this, where we put the aj from this part to that part in the equal to, and this is the ai, which is called the components of the contravariant vector. So this is the first one where we are coming to know about the contravariant vector of rank 1, obviously rank 1 because we are using one script of that. Yep. A quick example, if x be I be the coordinate of a, say for example, n-dimensional generalized space, then we have to show that dxi are components of the covariant vector. Simple. We use the same x1, x2 up to xi for an x coordinate system, and x prime 1, x prime 2, xn up to the y coordinate system. We get this, and using the rules we get this, right? And from there we get this. So it is a law of transformation of contravariant vector, and obviously dxi are components of contravariant vector. So this is quite simple, just a basic kind of a demonstration which will lay things more solid for the listeners. We start with the covariant vector part. So we follow the same rule, say ai, and we take it up to an, right? So this is x and y coordinates. So a sub I goes up to 1, 2, 3 dot 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 up to n. This is the n functions of the coordinates of x super 1, x super 2 up to in x coordinate system. If the quantity is same, if it is transformed to this in y coordinate system, then according to the rule of transformation we get this and we get this. And just by flipping, I just wanted to show that how this OR happens. So ai are the components of the covariant vector. Just a quick note to the viewers that a superscript is always used to indicate a contravariant component, and a subscript is always used to indicate a covariant component. In case if you find that I have made any kind of an error, just my kind apologies for that. It is not intentional, but maybe due to complex equations I have made it in an error, so you can just forgive me for that. So now we go ahead and we understand the tensor algebra and the tensor for rank 2. So it won't be too difficult because we will follow the same thing. So let A super I this be the n square functions. Now it is rank 2, so obviously it would be n square functions. And if the quantities of A superscript ij are transformed into aij, I mean to say a prime ij in y coordinate system with coordinates x1 prime and so on, obvious, then according to the law of transformation we get this. So and then we call this aij are called the components of the contravariant rank tensor of rank 2. So that is why on the left hand side extreme of the screen I've just underlined it. Going ahead with the covariant tensor of rank 2, we will follow the same one. Let A, then the ij comes below because it's a covariant and it goes to x coordinate system. And in case the quantities aij are transformed into y coordinate system with x prime 1 x prime 2, then according to the rule of transformation we get this, and this aij are called the components of the covariant tensor of rank 2. I hope this is quite easy, quite fine, laying down the rules how things happen. Now with this part, when we start with the metric tensor, we will deal with the invariant symmetry one by one, and I will just show you how we frame the part. First of all, what we would do is that we are going to prove that metric tensor is a covariant symmetry tensor of rank 2. Now in order to do that, what I will do is that first of all I will take a slow step by step. This would be in the x coordinate system and x prime I would be in the y coordinate system. Then the metric of ds square, which is this original metric, is being transformed here, right? Obviously it is transformed in the separate part. So now you need to note that because distance is a scalar quantity, right? So this would be equal to this. Now I will be proving this into 3 steps. Okay, first I will prove dxi is a contravariant vector. Second, this one is a g sub ij is a contravariant tensor of rank 2. Then I will prove that gij is a symmetric. These would be the steps. So first of all, let us start with dxi as a contravariant vector. So just to show that gij is a contravariant tensor, since this part, right, and then it comes to this part. So this is nothing to explain, actually we are following with the partial derivative and the tensor rules. We get this. So it is a law of transformation if you understand of a contravariant vector. So dx super I is a contravariant vector, this one. So first part is done. Next we go with gij as a covariant tensor of rank 2. So since you can see this and this, this is equal to this. So from this equation, which has marked it in box, right, I have taken the earlier equation into account. We get this. You can just do your own calculations. We get this and we get this. And now since this and these are equal to each other, and I and j, just note that they're dummy indices. If you're really wondering that what is a dummy indices, you need to look back to the tensor part. These are the basics of tensor. So there's something which is called a dummy indices we generally use. So this is equal to this because we have cancelled out and we are not taking into account the dummy indices, which leads to this, right? Now what we will do in the second part is that this one, you see dx sub k and l, these are arbitrary, so it would lead to this and it would finally lead to this. So which proves that this one is a covariant tensor of rank 2. So these are just the mathematical steps. You can do your own homework and you can just look into the calculations. So this is how the second part is being proved. Now we will prove that gij is symmetric. Now this is can be written something as this, right? This is, I'm following the skew-metric rule. This one, why? Because this is skew-symmetric. This is symmetric, and then the next part is skew-symmetric. So what happens because of this? We will get obviously this, which you can calculate from the earlier equation which I have taken, and then we get this. So we interchange the dummy indices. Now you see, I told that we have got dummy indices, but we have interchanged the dummy indices, and we have got this one, bij dx superscript I and dx superscript j, and this, right? So you can just work out with your equations. I think that there's nothing more that I can explain. I have interchanged the dummy indices. Now because this one is a skew symmetric, I hope we all know what is a skew symmetric, this becomes equals to 0, and because it is 0, we take this equation. You can go back to my previous slide and just check in what this equation is. I've just taken this fourth equation and I've taken this as 0, and I get this part, which is dxi and j. These are arbitrary, right? Because they are arbitrary. So now you see gij is symmetric. Why? Because a sub ij is also symmetric, and we have shown that. You can go back and you can check. So that is why gij is a covariant tensor, symmetric tensor of rank 2. This is called the fundamental covariant tensor. Right, so I think that we are quite okay, and we are just following the rules, and we are doing the mathematics in order to let you know what is a covariant tensor of rank 2. We are just left with the last part. So yeah, so we have done with this part. dxi we have proved as a contravariant vector, covariant tensor of rank 2, and gij is symmetric. Now all this taken into account, why I have done that, this is just to follow the 3 steps. How do we do that? Because we now want to show you this, because this is the crux, isn't it? We have seen that how with the dot product things changes using the contravariant as well as the covariant, but most important is that metric tensor remains invariant, which makes general theory of relativity so interesting, so that we can measure anything on a manifold on the space-time. Now in order to prove that, what I will do is that I will take this one as x coordinate system and x prime I in the y coordinate system, and we know that gij is a covariant tensor of rank 2. Then we also know this, which implies this and this, and further calculation leads to this part, right? So you can just check in what the calculations are going on, and then it shows this and further this. So you see now that this, if it is equal to this, then obviously that is invariant in nature. So that is why we say gij, this one which I showed right at the beginning, is an invariant in nature, and that is why all the calculations and everything becomes so easy in the metric in general relativity. So this is the crux, this is the bottom line of making the calculations to show that why this is in an invariant nature. You can take a pause, you can take a notes, you can take a screenshot of all those things. That's it. I wanted to show you this last exercise just to make you understand that when we talk of metric, different coordinates, different metrics, can we find out a metric for cylindrical coordinates? If so, how? Just follow me out. We know that this is the Cartesian coordinates, and let us suppose that we take the prime notation as the cylindrical coordinates, and we know this is, yeah, it is for the cylindrical coordinate part, so that this one becomes to x1. We are equating this with x1, x2 and x3, and this is another one, this is x prime 1, right? So what we will do is that we know that this is the metric tensor of Cartesian coordinates, and this is the metric tensor of cylindrical coordinates. And in Cartesian coordinate, this is how the coordinates go. This is very similar, so I'm not going to explain further things. So now what we do is that we write ds square in this quadratic form. Now if you really feel that this is something that you need to know, you can go back to my previous video on metric tensor and check things out. Now comparing these two equations, the first one and this one which I am showing, we get this, right? Because all this will become to 1, and that is why 1 2 will be equal to 1 3, 2 1 will be equal to 2 3, and so on equal to 0. So once we do the transformation, we will get this. Since gij is a covariant tensor of rank 2 and we will, yeah, I've written Gij is a covariant tensor of rank 2, and we put ij etc equals to 1. Now what I am going to do from now on is that I'm going to put the value of I equals to j equals to 1, then 2, then 3, so that we can arrive to the final coordinate for the cylindrical part, cylindrical coordinates. So let us put it for 1, we get this. Now we know that this is equals to 0, so obviously this becomes evident, right? So we are putting, remember, the value to be 1. Now since x equal to r cos theta, y equals to r sin theta, and z equals to z, so what happens is that putting this value we get this, right? And because this equals to 1 and g prime 1 1 also equals to 1, we get the value of g prime 1 1 as cos square theta plus sin square theta plus 0. That's quite simple. So we are still continuing with the value of 1, so let it be here. Then what we do is that we put the value as 2. So what we see is this one, right? You can just check on the calculations in case I have tried to make it as accurate as possible. Now since this is 1, so obviously this will become to 1, and then we see this one equals to r sin theta, this one, and this will obviously become to 0, right? So we put g prime 2 2 as this, and we get this, and g prime 2 2 as r square. So this is up till putting the value ij equals to 2, and obviously we expand it and we open it to r sin square theta, the minus sign gets cancelled and it comes to positive. Now if I put the value 3, how does it become? The g prime 3 3, it gets to this, and we get this, right, equals to this, and we know that since these equal to 0, so obviously g prime 3 3, yeah, equals to 1. So this is equals to 1 and this one becomes to 0 finally. So 1, 2 and 3, all the values are done. So the metric tensor in cylindrical coordinates is this one with 1 2 3, which is this, and since this equals to 0, finally we get this. So that is quite a simple, pretty fast exercise in which we see that how we arrive at the values of spherical coordinates. We derive cylindrical coordinates, we derive the metric from there. Now just to summarize the entire video, see the basic idea of my making this metric tensor part 2, you can call, is to make you understand that where do we stand when we are moving through the Einstein's general theory of relativity or the field equation. Now see, we all know what this equation is all about. This denotes the Ricci curvature tensor, which is explained in my lecture in general theory of relativity playlist. This is the metric tensor which we just completed, right, the first part and the second part, and this is the scalar curvature. This we know is the cosmological constant, sometimes people call Einstein's greatest mistake, anyway up to him. This is the speed of light in vacuum, c4. Why this c4? In order to maintain the 4 dimension, we are not going into details. And this is the stress energy momentum tensor, where it actually is the matter movement across the space. We are done with this. We know what these are. We know, I would say, more or less little bit of details. You can check out my lectures in general relativity. What we know also, this is the good old gravitational constant of Isaac Newton. Now this part actually, if you say why this 8 pi comes into the play, this is to recover Newton's law of gravity for small static masses. What I'm trying to tell is that the Einstein's field equations under certain conditions get reduced to Newton's law of gravity or Newton's equations, and Newton's equations, once it is moving into the relativistic arena, it expands into Einstein's. So both of them are, kind of a complementary to each other. Now if we take this equation and we follow this g by c4, this is for the dimension reasons. If you remove g by c4, the entire equation falls apart. And this one, 8 pi, is called the 4 pi, that is for the steradians. So that is how the 8 pi comes. I'm not going into the derivation right now. What I mean to say is that you see that at low velocities, when Einstein's equation, we consider the speed of light etc. must reduce to that of Newton's. So the weak field limit of Einstein's equation gives the Poisson equation, which is that 8 pi for the Newtonian gravitational potential. So this is just to summarize that we have finally arrived at the understanding of Einstein's field equation except the 8 pi factor. Now if you look into my previous video in metric tensor, I have shown that if we take Isaac Newton, we get 1. This is not easy, I understand. This requires further derivation. This is the second law, and this is the law of gravity. If we consider the gravitational potential, we might write into this, right? This part is reduced to this. You see, second law of second law of Newton's second law actually get reduced to this. Why? Because this is the typical equation of geodesic, and geodesic, because it what I would say, it refers to movement. Obviously, second law is also something which is related to that. And look ahead on the right hand part of your screen. You will see this gets reduced to the Einstein field equations, the gravity, the entire gravitational potential considering the nebula square and phi equals to 4 pi g rho. This gets reduced to Einstein field equations. So on the left hand side, so I can say that it is under the non-relativistic limit. This leads to the Poisson's equations, and this is actually the second law. So that's it. I just wanted to give you a brief idea that metric tensor, because it relates a lot with the kernel of general relativity, Newton's law also under non-relativistic limit goes into this. It reduced to geodesic equation, and this reduced to Einstein field equations. So under certain non-relativistic physics, low masses, things moving pretty slow, and a little bit of sloth movement, these can be reduced to this. And that is how the wonderful equation of the physics stands, that each of these equations can be reduced to this and further expanded to this. That's it. I don't want to extend further about this video. So what I'm doing is that in the next video I will be coming with something which is called a space-time curvature. I have just a note to the viewers, I have deleted my space-time curvature because I admit it was horrible. I really admit that it is horrible because there have been usage of music and things were not clear. I received a lot of feedback from you. Good. It is good to get criticized because I am redefining space-time curvature in a better way, and I'm coming up with a with a video on general theory of relativity which requires minimal mathematics. Just watch it out. So stay safe, stay happy. Put up your like and put up your comment in the video, in the subscribe comment section, and do let me know what are the next videos that you really want to know. I will make it for you. Thank you. Bye. Stay safe and stay happy, and have a nice weekend ahead. Bye.